And so we're going to start with this idea of Henry's law, and it's actually going to dovetail very nicely into our other discussion for today, and that is getting started talking about gases and gas laws. Now, Henry's law, I want you to know, as far as Henry's law is concerned, yes, there is a way to quantify it, as evidenced by this equation. This equation says that the concentration of gas dissolved in a liquid is equal to some constant value, the Henry's law constant, and the partial pressure of the gas above the solvent. Now, again, we could quantify it that way. I'm not asking you to, but I want you to think about more along the lines of is, as far as gas solubility goes, there are really two things that we can think about in terms of what will make gases more soluble in liquids. And Henry's law has a lot to do with this. Now, the first factor is temperature. When we see increases in temperature, we're going to see decreases in gas solubility. And that should make some sense to us, given what we know about Raoult's law, given what we know about rates of evaporation, that kind of thing. When we see these increases in temperature, the kinetic energy of the molecules in the liquid are going faster as well. It's going to be a lot harder for those liquid molecules to surround those gas molecules and keep them dissolved. And so as a result, we see greater escape of gases and less solubility. The other factor in there has to do with pressure. Now, this is the one that's a little bit more difficult to understand until we give it some context. And the context I'm going to give you is this. Take your average can of soda or bottle of soda. When it's unopened, there is a ton of carbon dioxide that is dissolved inside of the liquid here. And the reason for that is because so long as it stays closed, the contents in here have been pressurized, meaning in addition to pouring in the liquid, they will insert high pressures of gas and then seal it up. And that's why when you first open the can, the first thing that happens is you hear that outpouring of gas. Now, it's also why when you pour it out, the first thing that happens as you're pouring it is that most of the gases begin to escape. And so what we're going to do is we're going to do a little bit of a demonstration here. I've got 2 cans of soda. This first one I kept in my fridge all night. And we can see that, let me turn off my background here for a second. So we can see in this first one, this is the cold sample. And if you look closely, and it's going to be hard to see on the camera here, but you can see that there are still some amount of bubbles there kind of hanging out on the top. Now this second can, this one was hanging out in my garage all night. So it's considerably warmer. And so the first thing that I note is that there's a heck of a lot more fizz here as I'm pouring. And that's because it's warmer overall. The other thing I can notice, and I don't know if this is coming through on your side, if it is, that's great. If not, you can see a considerable number of bubbles here in this particular can that was warm compared to the one that was cold.
Mm-hmm.
So if I hold them side by side, the one to your right was the warm can. The one to your left was the cold can. And we can see that the majority of the bubbles in deep summer months when my garage is insanely hot, we had a relatively cool day yesterday. So this is actually measuring at 24 degrees, which is 75 degrees Fahrenheit. So there's still about 20 degree Fahrenheit, 10 degrees Celsius difference between the two. But the primary difference we can see in terms of our Henry's Law discussion is that the fizziness, and we'll come back and look at these in a little bit just to see how it's changed over time. But overall, we can definitely see that in the can that was warmer, which again is the one here on your right, in the can that was warmer, we can see that there are far more bubbles that are undissolved and are looking to escape. Whereas in the can that was colder, we see a lot more uniformity because there is considerably more dissolved carbon dioxide. So that's really what we kind of walk away with Henry's Law here is, can we see that difference in dissolution? And so this is probably the most common application that we can think of in terms of the idea of pressure versus temperature, pressure versus dissolved gas. Another common way is to look at the concept through the eyes of looking at moving water versus non-moving water in terms of like swamps and that kind of thing. Because in swamps where we have a lack of moving water, we have stagnation, we tend to have warmer climates, we see far less dissolved oxygen, and that's ultimately why plant life kind of suffers there. And so that's really all that we wanted to look at from the standpoint of Henry's Law. And that is the last thing in our chapter 11 discussion. So any questions about that before we move on to talking about other properties of gases?
No.
All right, so the other thing that we're going to be looking at today then is we're going to start our look at chapter 10. And chapter 10 is the last full chapter that we will be looking at in this course. In chapter 10, we are going to be exploring gases and gas properties and some other key attributes of gases. And if you recall back to chapter 1, when we started talking about the idea of gases, what we have to think about is we know that gases are different from liquids and solids in a lot of ways. But probably most characteristically, gases are unique to other phases of matter because they lack shape and volume. They have a uniformity to them. They can fill any container. Unlike liquids and solids, they actually exert a pressure. And we know that with regard to volume, their volume will change significantly with temperature and pressure changes. And this is different than liquids and solids. We know that liquids and solids will expand and contract with temperature, and maybe to a slightly smaller degree with pressure. But the magnitude of it is not nearly the same. We also know that they mix uniformly with each other. and their densities are quite low. So those are our gas properties. Now, the purpose of this chapter is to try to explain some of those gas properties and then use our knowledge of those properties to ultimately make some determinations and do some calculations regarding those properties themselves. And so when it comes to describing gases, what we can look at are 4 primary parameters that we can use to describe gases and ultimately their properties. We can describe a gas by its pressure, that is, how much force does it exert on its surroundings. We can describe a gas based upon its volume, how much space does it take up. We can describe a gas based upon its temperature, how fast are its molecules moving. And we can also characterize a gas by the number of molecules, the number of particles that are present. And so these 4 parameters and the interplay that exists between the parameters. So how does temperature impact pressure? How does the amount of gas impact volume? Those kinds of things can be explained and are largely attributed to this kind of grand theory of gases. And the grand theory of gases we're talking about here is something called the kinetic molecular theory of gases. And so the kinetic molecular theory of gases goes like this. In the kinetic molecular theory, we have to assume that gas molecules are A, small. So small, in fact, that we can assume that their tiny volumes compared to the container's volume is practically negligible. So when we estimate the volume of a gas, we usually just describe the container that the gas is in. And we can do so because the collective volumes of all of the gas molecules in a sample of gas relative to the volume of the room is practically nothing. We can also assume that because of the way that they're spaced apart, gases in general do not interact with each other. There are no real significant intermolecular forces that exist between gas molecules. And the reason why is they are far apart from each other. Those gas molecules are in constant and random motion, meaning they are moving throughout the container consistently, constantly, and randomly. And what we mean by randomly is their motion is not impacted by external forces. So they move in straight line motion according to their own kinetic energy, and they will change direction or change momentum based upon what they interact with. So if they collide with something, they will change direction based upon that collision. And that gets us to the 4th part. When they collide with things, those collisions will be elastic collisions. Now, can any of you tell me what an elastic collision actually looks like? What does that mean when we say that a collision is elastic?
They bounce off each other.
Okay, not only do they bounce off each other, in an elastic collision, something is conserved.
Mechanical energy.
Exactly. So all the energy that came into the collision comes out of the collision. That's what an elastic collision means. So elastic collisions obey that law of conservation of energy. And so we don't see anything happening in terms of lost energy, lost speed, those kinds of things. And the last thing, number 5 here, their average kinetic energy is proportional to their absolute temperature. And remember, absolute temperature, what we're referring to there is Kelvin. So when we describe the energy of a gas and relate it to the temperature, we are relating it to degrees in Kelvin. And so, again, since we don't usually measure things in Kelvin, we have to take that into consideration along the way. We have to make sure that we convert our energies to Kelvin before we start using these temperatures to try to make relationships between the properties. So that's the kinetic molecular theory. 5 crucial and key statements that help us to describe gases and their behavior. Now, what we're going to get into next is how we use this theory to explain some of the relationships that exist between some of those parameters on the previous slide. And so the first thing that we're going to look at, I want to point this at you. What is the relationship between the mass of a gas and how fast that gas moves? And so take a couple of minutes, talk amongst yourselves. So if you are muted, please unmute and try to come into the conversation. What's the relationship between the two?
Momentum.
I think the mass of a gas is like the overall energy, but like how fast it moves depends upon depends on the amount of heat that is being applied to the object. I could be wrong, but
I think that the heavier the mass is, the slower the object moves, or the gas moves, and the lighter the gas, the faster it moves. And that's just like with any object practically. Like a heavier bowling ball is gonna roll down the lane slower than one that's lighter.
that's true.
Okay, so we're on the right track. Now, to some of the points that were being mentioned, if we assume that the gas temperatures are all the same, then what we can start to look at is what we're really talking about here is with speed of motion, we're looking at kinetic energy. And so if we have the gases at the same temperature, we would anticipate, based upon postulate 5 of the kinetic molecular theory, that the gases themselves are going to move and have the same kinetic energy. Now, kinetic energy, if you've had physics, you will know that kinetic energy is equal to 1/2 times mass times the velocity squared. Well, given that relationship, we can see that mass and squared velocity are indirectly related to each other, inversely proportional. If the mass is going up, the velocity, the speed, has to go down by a proportionate amount to keep the kinetic energy even. And if the mass goes down, the speed will increase to accommodate that, to keep the kinetic energy at a constant value. And so Malaz's statement overall is correct. The heavier the gas is, the slower it's going to move. The lighter the gas is, the faster it's going to move. And we can show this. This graph here shows the average particle speed for a number of different samples of gas. And so what we have here is, this is a distribution. So the red distribution here, this is all of the different particle speeds that a sample of hydrogen can have at a given temperature. The red line, and each one of these has a line, that is the average root mean square velocity for that particular gas. And so you can see that for hydrogen versus helium, we have a considerable increase in speed. And helium versus nitrogen and oxygen, we have increases in speed as well. The heavier objects, so you can see oxygen and nitrogen, which are considerably heavier than these two gases, have much slower root mean squared velocities than the hydrogen and the helium do. Now, we can quantify this and describe it through a property that is either known as effusion or diffusion. Now, diffusion is probably a term that you've heard of. Again, if you were familiar at all with osmosis before yesterday, you were probably familiar with diffusion as well. Diffusion is the movement of pretty much any substance from an area of high concentration to an area of low concentration. And so to that end, diffusion is just the movement of a gas usually as it spreads out from its origin to other parts of the room or other parts of the atmosphere. Where we see this the most often is the idea of odors. You're at home, your parents are making dinner, and you can smell it when you walk in the front door because it's been cooking on the stove for a while, and the good odors of that dinner are spreading throughout the house as they are cooking. That's diffusion. Effusion is slightly different. Effusion is, let's imagine that we have a gas trapped in a box, or we have a series of gases trapped in a box like this. And then I take and poke a small hole in the side of this box. Maybe I'll make it a little bit bigger. Now, what effusion is how quickly will the molecules inside of this box find their way out of the box through this hole? And the answer there comes back to this idea of this relationship between mass and velocity for a gas. We call it Graham's law. Graham's law, which applies to diffusion and effusion equally, says that the rate of diffusion or the rate of effusion is inversely proportional to the square root of the molar mass. So if I'm looking at trying to compare rates of effusion, so how quickly does the gas get out of the box? Well, the amount of time that it takes, the ratio of times is going to be equal to the ratio of masses with the square root. And so if I have a time here, so if gas 1 is half of the mass, then it would take the square root of 2's time. It would take 1 over the square root of 2 times as long as the second gas would. Now, the distance that a gas goes, as far as diffusion is concerned, well, that is, and this formula is actually incorrect. Let's fix that. The 1 and the 2 here are reversed. a heavier gas is going to travel less distance than a lighter gas will. And so there is a reversal here. So if I have my heavier gas here, the lighter gas is going to travel twice as far. So this is something that we can do. There are some practice problems in our gas laws examination in our one of our post lectures about Graham's law, and so this is what you'd have to do. Again, it's relatively straightforward. The real key there is that it's inversely proportional, other than including that square root part. Now, other questions that you can be asked follow along this line of thinking as well. List the following gases, which are all at the same temperature, in the order of increasing rates of diffusion: helium, krypton, nitrogen monoxide, and oxygen. Now, the way to attack this and handle it is I need to know the molar masses of each of these gases. That's really what we're after here, because if we're just looking qualitatively, that is without numbers, at their rates of diffusion, then we know that the fastest gas is also going to be the lightest gas, and the heaviest gas is going to be the slowest. So the molar masses here for each of them: for helium, it's 4.003 grams per mole. For krypton, it is 83.80. For nitrogen monoxide, 14.01 plus 16, 30.01 grams per mole. And for oxygen, it is 32 grams per mole. So here are my 4 molar masses. Again, if I'm putting it in order of increasing rate of diffusion, I'm going to start with my slowest and work my way up to my fastest. So krypton weighs the most, so it is going to be the slowest. Oxygen is the next heaviest, so it's going to be the next in line. Nitrogen monoxide would be next, and then finally helium. And so for problems like this, where we're just doing ranking and rank order, it's really a matter of slowest to fastest or fastest to slowest, and we use molar mass to determine all of that. All right, any questions here?
No.
All right, so let's do something that's a little bit more quantitative then. Calculate the molar mass of a gas if equal volumes of oxygen and an unknown gas take 33.25 and 4.60 minutes respectively to fuse through a small hole at constant temperature and pressure. Okay, so for that, we're going to have to use this equation here. Time 1 over time 2 is equal to the square root of mass 1 over mass 2. Okay, so if I use oxygen as my time 1 and my unknown as time 2, then I can set up this equation relatively straightforward. I've got oxygen 3.25 minutes divided by the unknown's time, 4.60 minutes. And that's over the square root of oxygen gas, which is 32 0.00 grams per mole. And we don't know the other molar mass. Now, the easiest way to handle this is to start by squaring both sides to get rid of the square root. So if I square both sides, I'm going to do the division first. 3.25 divided by 4.60 quantity squared. I get 0.499, and that's equal to 32 grams per mole. Over X. And so my next step is to isolate the X. So I'm going to switch the denominator and the other side of the equal sign. 32 divided by 0.499. My unknown has a molar mass of 64.1 grams per mole. And that makes sense. After all, it diffused or effused slower, so we would expect it to be heavier. And so that's one of the ways that you can really check yourself when you're doing these kinds of calculations, is you have to make sure that the number makes sense. If it's effusing slower, if it's diffusing slower, regardless of what it is that it's doing, then it better be heavier. If it's not, then you need to look at your equations and you've got one of these flipped over, and you need to fix that. Any questions about this example?
No.
Okay, so let's take a minute and talk about pressure. Now, pressure, by definition, is the force exerted on an object per unit area. When it comes to gases, what we usually end up talking about the most is something called atmospheric pressure. Now, atmospheric pressure is something that is being exerted on you right now. Atmospheric pressure is the amount of pressure that is exerted by all of the gas molecules that make up our atmosphere. And so anyone who is anywhere has gas on them, exerting a pressure on them at that particular moment. Now, we can measure atmospheric pressure using something called a barometer. A barometer measures atmospheric pressure using a device similar to, although not exactly the same as this. Now, this is kind of based on the original model by Evangelista Torricelli, where you had this open pool of mercury and this evacuated glass column to measure the height of the mercury in. Modern barometers are a little bit more sophisticated than that, at least the ones that use mercury. Most barometers that you would buy commercially now use electronic sensors to detect pressure from the atmosphere, as opposed to actually exposing you to mercury. But there are some mercury barometers still out there. In fact, our lab at Vincennes University has one that we do use to measure atmospheric conditions from time to time. But the way that it works is basically you've got two forces at play here. The column here is evacuated. So there's no gas pressure whatsoever in the top of this tube. The only thing that is pulling the mercury down is its own weight, its own gravity. So what you've got is an interplay of two competing forces. You've got atmospheric pressure pushing down on the pool of mercury, which in turn pushes mercury up the column. And then you've got the weight of the mercury itself pulling the mercury down on the column. And so when the two reach an equilibrium with each other, where their forces are actually equal, that's what we can measure as the barometric pressure. Now, when it comes to pressure units, we can see that there are several here in this table that are of interest to us. Where we tend to focus the majority of our attention is only on some of these. Obviously, we've talked a little bit in osmotic pressure about atmospheres. That's going to remain of interest to us. Millimeters of mercury, or torr, these are the same thing. Torr comes from an abbreviation of Evangelista Torricelli, Torricelli's last name. And so this is thought of as kind of a tribute to him for the work he did in inventing the barometer and kind of bringing about a greater understanding of the way that we measure pressure. In the United States in particular, we do see units of PSI and inches of mercury. PSI is most commonly used for things like tire pressures, gauge pressures. When we talk about gases in terms of things that are mechanical, when we talk about them in terms of things like gas tanks, air tanks, PSI tends to be our measurement system. Inches of mercury tend to be used here in the United States for weather forecasting, to get an idea, get a sense of what atmospheric conditions are and how they're changing, because that's usually a good sign of what's going on as far as the weather is concerned. These other units, physicists tend to focus on pascals. Pascals or pascals are named after Blaise Pascal, the physicist. We don't see them used very often. For one reason, if you look at the interplay here, 1 atmosphere of pressure is equal to 101,325 pascals, which means that we're dealing with pretty significant numbers. For atmospheric pressure, or for anything involving large quantities of gas, pascals really are impractical. Kilopascals are a little bit better, but still not terribly useful to us. Bars have picked up some steam. The IUPAC is actually rephrasing some of our conditions in terms of bars. You can see that bars and pascals are essentially the same in terms of number, but the magnitude has been flipped. But we are starting to see bars being used far more often. But for us, we're going to mostly stick with atmospheres, millimeters, and torr. Those are going to be the primary pressure units that we use. Now, in addition to what I showed you with the barometer, we can also see that there are ways of measuring pressure of a gas individually. And what we can do is we can use them through something called a manometer. A manometer takes advantage of this idea of the movement of a height of mercury, but does so in a comparative sense. And what I mean by that is we can compare the height of the mercury before and after and use that to determine its pressure. So in a closed system where we have an evacuated tube here that is closed on one end, when we open up the gas, the amount of climb that we see in the mercury would tell us the pressure of the gas. Now, this is impractical for a number of reasons. We don't tend to see this method used as often as this one, where we have an open system, where instead of having an evacuated tube, instead of having a closed end, we just have a tube here that is open to the atmosphere. And so atmospheric pressure is pushing down on this side as opposed to nothing in the closed system. And then when we open up the gas, we can measure how does it do against atmospheric pressure. So if the gas pushes up on the open tube, we know that the pressure inside is greater than atmospheric pressure, and we can measure this height and basically add the height to the atmospheric pressure to figure out the pressure of the gas. If atmospheric pressure actually ends up pushing up against the gas, then we know that the pressure of the gas inside the tank is less than atmospheric pressure. And so we can subtract this height from atmospheric pressure to get the pressure of the gas inside the cylinder. So these are ways of measuring pressure kind of independently. But again, they really only work, excuse me, they really only work in the event that we have gas contained in a tank and we can measure it one direction or another. And so let's go ahead and take a short break here. It's 5 to 10. And when we come back at the end of our break, we'll get into some gas laws and some specific relationships between those parameters, which will set us up for kind of the rest of the calculations and things that we'll be doing for this chapter. So let's come back at 10:05 and we'll get started again there. But if we're talking specifically about a chemical reaction in any kind of way, or excuse me, if we're not talking about a chemical reaction, the amount of gas is going to remain relatively constant. If I'm just looking at a balloon, or if I'm just looking at a gas contained in a cylinder, so long as the cylinder doesn't get opened, the amount of gas is going to be relatively constant. And so if it's constant, then we can condense this a little bit, and this equation that results is often referred to as the combined gas law. Now, we use the combined gas law in particular for one particular purpose. And that is to monitor changes in a gas sample. And so its utility can come into play in situations like this. Let's say that we have a sample of oxygen gas at half an atmosphere, and it occupies a volume of 10 liters at 0 degrees Celsius. What is the pressure of the gas if it is at 15 liters and 25 Celsius? So again, a quick way that we can evaluate our position is we look at our parameters. We see that our volume has increased, but so has our temperature. And what we want to know is what happens to the pressure. Well, looking at this, we can say, okay, we see that the volume has increased by 50%. The volume is much, much larger now than it was before. Temperature hasn't increased by the same amount because, again, we've got to think about things in terms of Kelvin. 0 degrees Celsius is 273 Kelvin. 25 degrees Celsius is 298 Kelvin. So we saw a 50% increase in volume. Looks like we're getting maybe a 10% increase in temperature. Since pressure and volume are inversely related, and temperature and pressure are directly related, the impact on the volume is going to be greater. So we would anticipate that our pressure is going to go down because of the higher increase in volume than the increase in temperature. That would be our prediction. Now let's see if it actually comes to bear. The equation here is P1 V1 over T1 is equal to P2 V2 over T2. Our initial pressure is 1/2 of an atmosphere. Our initial volume is 10.0 liters. Our initial temperature is 273 Kelvin. We are trying to find the second pressure. Our second volume is 15.0 liters. And our second temperature is 298 Kelvin. And so if I put all of this together and I start working out the sides of the equation, 0.5 times 10 divided by 273, I would get 0.0183 atmospheres times liters over Kelvin. On the flip side, I've got P2, 15 divided by 298 is 0.0503 liters over Kelvin. So if I divide both sides by the 0.0503 liters over Kelvin, I get P2 as equal to 0.364 atmospheres. So our prediction, based upon the other parameters, was that the pressure was going to go down because the volume increase was significantly better than the temperature increase. And that has come true. We saw 1/2 of an atmosphere turn into 0.364 atmospheres as a result of these other changes in parameter. All right. Any questions about this example?
I don't have any.
No.
Okay. Now, the other direction that we can go, so if you go back to our combined gas law, we had this equation, PV over NT is equal to a constant. Well, if we take that idea and we actually apply a value to that constant, what we have is something called the ideal gas law. Now, the ideal gas law uses a universal gas constant. The universal gas constant, 0.08206 liter atmospheres per mole Kelvin. Now, if that sounds familiar, we use the same universal gas constant for osmotic pressure yesterday. It should be noted that there is another version of this that we can use. Involving millimeters of mercury or torr. And so notice that everything is the same in this. Other than the pressure unit. The pressure unit is the one thing that changes in each of those cases. And the pressure unit P here would vary. So if I used this one in the middle, it would give me a pressure in millimeters of mercury. If I use this one at the bottom, it'd give me a pressure in torr. Otherwise, this equation is universal in that kind of sense. Now, where we use the ideal gas law, we use it primarily to describe a gas in terms of amount of gas, or we can use it to convert between volume and moles in a chemical reaction. And so that gets us more into gas phase stoichiometry, which again, we'll talk about more tomorrow. But the difference between the combined gas law and the ideal gas law. A combined gas law we use primarily when a gas is changing in terms of its temperatures changing, its volumes changing, its temperature is changing. The ideal gas law we tend to use when we are describing a gas. So I want to know how much of the gas I have, or I want to know if I want to know, okay, how much volume does half a mole take up at 30 degrees Kelvin and 400 atmospheres of pressure, or whatever the case may be. This helps me to describe a gas as it is at this particular moment. And that's different from the combined gas law. The combined gas law tells us, okay, how does this gas change as we go from one zone to another? Now, as I mentioned before, the value of that universal gas constant can change. We tend to focus on these two units here. SI units are available as well, using cubic meters and pascals, or more commonly liters and kilopascals. This particular version of the unit isn't going to be something that we will use very much in this course. If you have to take Chem 2 along your way, this value of R is often used as a matter of energy. If you combine some of these quantities into each other, you can end up getting the energetic unit joules. And 8.314 is the measurement of joules per mole Kelvin for R when we're talking about energy. So I don't know how many of that will apply to you, but it is something that you will see. And so again, if you have to take Chem 2, or you take physics and you have to use this value of R, this particular unit will come again, because meters cubed times pascals is joules. But for our purposes, we're mainly going to stay in this lane down here and use either 0.08206 for atmospheres or 62.36 for millimeters of mercury or torr. So let's do a couple of calculation examples. How many moles of gas are contained in a 4-liter container at STP? Now again, STP is 273 Kelvin and 1 atmosphere of pressure. And so there are two ways that we could solve this. We could use the ideal gas law, where we have PV is equal to nRT, and I could just start to push in 1 atmosphere times 4.0 liters is equal to N times 0.08206 liter atmospheres per mole Kelvin, and 273 Kelvin. I could do that. And the end result would be pretty much the same as, since we're in STP, remember Avogadro's law. 1 mole of gas at STP is equal to 22.4 liters of space. So we can actually do this a much simpler way. 4.0 liters and knowing that there are 22.4 liters in 1 mole, 4 divided by 22.4 to 2 significant figures is 0.18 moles of gas. Now, if you had solved this out using the ideal gas law, 1 times 4 divided by 0.08206 divided by 273, you would have got the same to 2 significant figures, 0.18 moles of gas. So either way would work in this case. This is a special circumstance, however, because we are at STP. At STP, this relationship holds up. But if we were not at STP, we would have to use the ideal gas law like this. We couldn't just do a direct conversion using this equation. Any questions?
No.
No.
All right, let's take a look at another example. Calculate the pressure of 4 moles of methane gas in a 12.3 liter container at 25 degrees Celsius. Okay, so again, this is a scenario where we're being asked to describe a gas. The gas isn't changing temperature or pressure or anything, so we're going to use the ideal gas law. PV is equal to nRT. As far as our pressure is concerned, we don't know. That's what we're trying to find out. We do know the amount of gas. We do know its volume, and we do know its temperature. We just need to convert it into Kelvin first. And again, converting from Celsius to Kelvin means we add 273. So we've got all of the values that we need. We just need to solve for the one that we don't have. P times 12.3 liters is equal to N, 4.0 moles, times R. Now, we haven't been told what pressure unit to use, so we can kind of use whatever one we want. For the sake of consistency here, let's use 0.08206 liters times atmospheres divided by moles times Kelvin, and 298 Kelvin is our temperature. So to solve, we're going to have to divide each side by 12.3 liters. So my 12.3 liters cancel, my moles cancel, my liters cancel, my kelvins cancel. I'm left with just atmospheres. So pressure is equal to 4.0 times 0.08206 times 298 divided by 12.3 to two significant figures. I'm going to get 8.0 atmospheres of pressure. Now, like I said, this didn't ask us for a specific pressure unit. I could have gone in any direction from here. I could have used 62.36 and gotten torr. I could have used 8.314 and gotten kilopascals. It didn't get specific with us, but more often than not, I go with atmospheres by default. Unless I'm in a situation where I'm measuring it myself. When I measure it myself, I'm going to use millimeters of mercury because that's how most pressure sensors. That's what most pressure sensors use. But otherwise, atmospheres work really well and give you relatively small numbers to kind of work with. You have less haggling over significant figures because you're not dealing with 550 or whatever. You have to worry about whether or not the last zero is significant. Any questions?
No.
All right, go ahead and try this one yourself then. You've got an experiment that shows that a 0.281 gram sample of an unknown gas occupies 127 milliliters of space at 98 Celsius and 754 torr of pressure. Calculate the molar mass of the gas. So the big hint here is that molar mass is equal to grams divided by moles. We've already given you the grams. Use your other parameters here to figure out the moles and then divide. So I'll give you a couple of minutes. When you finish or you think you have an answer, just go ahead and give me the okay, and we'll start going through it together. Okay, so how are we doing? Any questions so far?
I'm having trouble with the torr part.
Mm-hmm. Now keep in mind, torr is the same as millimeters of mercury.
Okay.
So your R value should still be 62.36 liters torr per mole Kelvin.
Okay.
Did you get 0.004?
For the moles?
Yeah.
Yes.
Never mind, I got it.
All right. Malaz, you do okay? All right, so let's start kind of piecing it together. We know we're going to need the ideal gas law. Our pressure in this case is 754 torr. Our volume is 127 milliliters, which would be 0.127 liters. We're trying to find N. R is 62.36 liter torr per mole Kelvin. And 98 degrees Celsius would be 371 Kelvin. So that's what our setup is going to look like.
Mr.
Go
Mr.
ahead.
Bro, I
Yeah.
got for that top, I got 0.0827. When I remember when I said I got it, it's because I divided the 62.36 by 754.
Okay.
I got that at the top, not the 62.36.
Okay, so this number here, the value of R comes from our universal gas constant. So if we use 0.08206 liter atmospheres per mole Kelvin, the value that we get here, the 62.36, is going to come from the conversion of atmospheres to torr. 1 atmosphere is equal to 760
Oh, okay.
torr. And so if you do that, 0.08206,
No, 0.0827, 0.0827. Because 62.36 divided by 754, because we got 754 torr.
okay, but 754 is the value that we measured. That's not the conversion.
Okay.
If you want to convert, you would have to convert both of these values to atmospheres.
Okay.
So if you'd gotten, but for the value of R, if we just use this equation straight up like this, all of our units match up. That's what we want.
Okay.
We want all of the units to match up. If we wanted to use this value here, the 0.08206, we would have to convert our pressure unit here into atmospheres, which means we would divide it by by 760.
Okay.
So you can do that. That's not a problem. But since we have this value of R already kind of there for us, it's a lot easier to just use it.
Okay.
So if we do the division, we would be dividing both sides by 62.36 liter torr per mole Kelvin and 371 Kelvin. Uh, 62.36 liter torr per mole Kelvin and 371 Kelvin. So we do all that. Everything cancels on the right-hand side other than N. My units of Kelvin, liters, and torr cancel on the left-hand side. And so I would get 754 times 0.127 divided by 62.36 divided by 371 to three significant figures. I would get 4.14 times 10 to the negative third moles for N. To find the molar mass, I need the grams and the moles. My grams was 0.281 grams. My moles was 4.184, or 4.14 rather. That's 10 to the negative third moles. If I do that, 0.281 divided by 4.148 times 10 to the negative third, I get 67.9 grams per mole. All right. Any other questions about this example?
No, I need to just remember the conversion thing.
Well, and the good news for you is that your values of R would be given to you.
Okay.
They're not ones you have to memorize, so they will be there. They'll be given to you.
I got everything. I got everything else but that 62.36 torr. I got the 371K plus two is 198 plus 273. I got that. I got the 0.127. I gotta remember the 754 torr and the 62.36 because I didn't know.
Yeah, and so
I thought you had to convert it, but I need to remember you don't have to, I guess.
no, you don't have to. And the reason why, take you all the way back here. Millimeters of mercury and torr are the same thing. So when we look at our unit of R, we can easily say that this is the same value for torr as it was for millimeters of mercury.
Yeah, it's just that one, because some of them problems, it is ATM, and you do have to convert it.
Well, if you're given ATM, you can use the gas constant for ATM.
Okay.
If you're given millimeters or torr, you can use the gas constant for torr. If you're given kilopascals, you can use that. Now, if you're in the position where you can't and you do have to convert, that's where the conversions list here would be of the most use to you. If you're given something in PSI, we don't have a R value for PSI, but you can convert it to atmospheres or into torr or any of those others. And keep in mind the transitive property applies here as well. If 14.7 psi is equal to 1 atmosphere and 760 millimeters of mercury is equal to 1 atmosphere, understand that they're also equal to each other. And so you could convert directly between them. So you could do something like this, where you have 14.7 psi in the denominator and 760 millimeters of mercury in the numerator, and do a conversion factor